we've already seen how to solve an exact differential equation. But what do we do if we have a differential equation in this form and it's not exact? In other words, we already know that the differential equation is exact if and only if m sub y equals n sub x. What if that's not the case? Well, if that's not the case, maybe we can ask, is there some function, mu of xy, which we'll call our integrating factor, which has the property that when we multiply it through on both sides of the equation, but of course the right side is already 0, that maybe this is now exact. In other words, maybe it's true that if this, the partial derivative of this, the partial with respect to y of mu times m must equal the partial of this with respect to x. That's mu times n. So this is that condition I just wrote down, and by using the product rule, we get that that condition is equivalent to this differential equation. Now, you can think of this as a differential equation for the function mu. Unfortunately, this is a partial differential equation for the function mu. And this could be a very complicated thing to solve, essentially as difficult as solving the original problem. So in general, this doesn't really help us too much, unless things work out very nicely and some sort of simplifying factor comes in. What could make things simple? Well, what could make things simple is if one or more of these terms happens to be 0. Well, how does one of the terms happen to be 0? Well, if mu is a function of just one variable, say x, then this term would equal 0. So we cross it out because d mu dy would be 0. And then what we're left with is mu times dm dy equals d mu dx times n plus mu times dn dx. Now here, if I just solve that for d mu dx, I get d mu dx equals this thing here, m sub y minus n sub x over n times the original function mu. Now here we'll still have problems because we're assuming here mu is a function of x, which is why I'm writing d mu dx just as mu prime. But in order for that to make sense, we have a function of x here, a function of x here. We need this function here, m sub y minus n sub x over n, to be a function of x. In other words, we need this to be entirely dependent on x and not have any dependence on the variable y. If we're so lucky that this function depends only on x, then we look for a solution to this differential equation, finding mu as a function of x that satisfies this differential equation, and we'll have our integrating factor. So this is what I had just said. We need this function, m sub y minus n sub x over n, to be a function of x. Well, then how do we satisfy this differential equation? This is just of the form mu prime equals, say, p times mu. We already know the solution is mu equals e to the integral of p works. This is something we already looked at when we were finding integrating factors in the simpler case of linear differential equations. So we can just use that here as well. Let's show an example to see how this works. This is our function m, and this is our function n. If we compute m sub y, we see immediately that m sub y is 3x minus 2y, and we compute n sub x is 2x minus y. These are not the same, so this equation is not exact. That means we can't just solve it right away, by finding a function c whose derivative with respect to x is m and whose derivative with respect to y is n. That won't work. But what if we compute m sub y minus n sub x over n? Here, this minus this is x then minus y. And we divide by n, which is x squared minus xy, and that quotient is just 1 over x. This is just a function of x. So then we create our integrating factor. Mu is just a function of x, and it will be e to the integral of m sub y minus n sub x over n, which is 1 over x dx. This is just log x, and e to the log x is just x, so I can use an integrating factor, which is just x. Then the equation becomes this equation here when I multiply through by x. We'll get 3x squared y minus xy squared plus x cubed minus x squared y. This one is now exact. This is our new m and our new n. I'm reusing the same letters, but let's forget the old ones and just pretend this was the equation we had to start with. In this case now, m sub y is just 3x squared minus 2xy, and sub x is 3x squared minus 2xy. So we verified that it's exact, and we knew it would be since we had computed the integrating factor precisely to make it exact. It's good to check anyway, in case we made any mistakes. We can find this function c now with c sub x equals this new m, and c sub y equals that new n. We use a standard procedure. We start by integrating this function with respect to x, and we get x cubed y minus x squared over 2 times y squared. I'll write that as x squared y squared over 2. And then we can add an arbitrary function of y. Because the partial with respect to x just makes the partial with respect to x of g of y is 0. So a function of this form makes this equation true. Now, how do we make this equation true? Well, c sub y then, the partial of this with respect to y, is going to be x cubed from here, and then we're going to have 2 times x squared y over 2, which is just x squared y, plus g prime of y. So what that tells us is, since that's already exactly what we need c sub y to be, that tells us g prime of y must be 0. G can then be any constant. And we can take g equal to 0. Because we're going to have an arbitrary constant coming up later. So what does that mean? It means we can use c of xy just equal to x cubed y minus x squared y squared over 2. And what does that tell us about the solution to this differential equation? When we integrate both sides, we get exactly x cubed y minus x squared y squared over 2 equals c, where c is an arbitrary constant. Just from integrating both sides of this equation. So I claim that this gives us the general solution. It is, of course, presented implicitly. One could solve for y to get an explicit solution. In this case, it would be algebraically something we could do, because we could get a quadratic in terms of y, which we could solve using the quadratic formula. But for now, I'll just leave it like this. You should check this just by using implicit differentiation and see that it tells you that this equation is satisfied.